All right, everyone, it is now 1 p.m., so I think we will go ahead and get started. Welcome to the HPC Best Practices webinar series, which is brought to you by the IDEAS Productivity Project, funded by the Exascale Computing Project. The series is a collaboration involving the U.S. Department of Energy computing facilities at Argonne, Oak Ridge, and Lawrence Berkeley National Laboratories. My name is Ashley Barker, and along with Osni Marquez, we will be your hosts for today's webinar, which is titled Refactoring EXAALT MD for Emerging Architectures. This webinar will be presented by Aidan Thompson of Sandia National Laboratories, Stan Moore, also of Sandia, and Rahul Gayatri from NERSC. So I'd like to just give you a little background from our three speakers. Aidan has worked in the Center for Computing Research at Sandia since 1997, first as a postdoc appointee, then as a principal member of the technical staff. He is one of the core developers of the LAMPS molecular dynamics code, and in recent years, he has become a leading developer of machine-learned interatomic potentials fit to large databases of quantum calculations. Stan is also a computational scientist at Sandia, specializing in particle-based simulation methods such as molecular dynamics and direct simulation Monte Carlo. He is a software developer of LAMPS and Sparta codes, and his research currently focuses on extending particle-based codes to use Sandia's COCOS performance portability library to run efficiently on next-generation computing platforms. And last but not least, Rahul Gayatri is an application performance specialist at NERSC and works closely with an application development teams to optimize compute-intensive kernels for future generation architectures. He's currently working with the LAMPS team in the EXAALT ECP project to optimize the SNAP module for NVIDIA GPUs. So just a few housekeeping items before I turn it over to these folks. We have sold over 100 tickets for this webinar. Everyone has been muted upon entry, but if you are having technical issues, you can put them in the chat window and I will try to address them. And then also we highly encourage questions through this webinar. We ask you to do that in the Google Doc. The link is on the slide I'm presenting. It was also sent in the email with the connection information. We just find it's a lot easier to address your questions in the Google Doc versus trying to do it inside of the chat window in WebEx. So with that, I'm going to turn it over to Aidan, and we will get started.
Thank you very much, Ashley and Osni, for inviting us to present this work. It's a pleasure to be here. So my name is Aidan Thompson. I'm going to start the presentation, then I'll hand it over to Stan. Both of us are at Sandia National Laboratories, and then Rahul will talk about more of the details, and he is at the NERSC facility at Lawrence Berkeley Lab. So the goal of the work is to refactor the EXAALT software stack to make it perform better on high-performance computing platforms. But by the way, can everybody see my slides okay? And can everybody hear my audio?
I am able to hear you and see your slides.
Great, thanks. So a little bit of high-level information on how the different parts of this work connect together. So this is all done within the context of the Exascale Computing Project. Within that, I am a member of the EXAALT ECP project. It's an application project, and the goal of it is to extend the power of molecular dynamic simulations for materials in 3 distinct dimensions, namely accuracy, length, and timescale, using exascale computing resources. And so there are very interesting aspects to this problem involving length scales and time scales, but the focus of the work we're talking about here today is accuracy. So we are trying to go from relatively inexpensive, relatively low accuracy interatomic potentials describing the interactions between atoms to much more expensive potentials that are fit to large data sets of quantum DFT calculations. And so the one that we're talking about here, of course, is SNAP, and I'll be talking more about that in detail. But in the context of ECP and EXAALT, the goal is to make these SNAP molecular dynamic simulations in LAMPS run many small MD replicas that can be combined together when spread over a large number of processors, to obtain information about the behavior of materials on very long timescales, and that's using the parse splice methodology that's developed by Danny Perez and others at Los Alamos. And I should mention Danny is the PI for the EXAALT project. So in terms of performance, what we are really now focused on is trying to improve the performance of the snap interatomic potential running in lamps on a single node of these upcoming architectures, many of which are based on GPU processor technology. And so everything really comes down to how well we can run MD on a single node of these machines. And if we can do that at a high performance rate, then we can expect to be able to scale that to very large numbers of nodes. An additional twist is that the COPA co-design project, which is focused on many different sub-motifs involving particle simulation methods, they chose SNAP as one of their targets for improving performance. And the nice result of that was that Stan Moore got involved as a member of the COPA project to really focus on improving the performance of SNAP in our LAMPS molecular dynamics code. So not to bury the lead, I want to summarize the result of all of that work over the last year on this slide, which represents on the x-axis calendar date, and on the y-axis is the EXAALT FOM, or figure of merit, which is a unitless number that is based on the performance of the original SNAP COCOS implementation on the full Mira machine. So in other words, how many atom time steps were we able to get on all of the Mira processors? This is the IBM BGQ machine at Argonne National Laboratory that I think is just in the process of being decommissioned. So that quantity, that performance represents 1, according to our EXAALT figure of merit. We were, of course, interested to know how this would work on GPUs, because Mira is a purely CPU machine. And so the first information we got on that was when Stan Moore and Christian Trott used the COCOS library that's available in LAMPS to build a first version of SNAP that could run on GPUs. And when that was completed and Danny Perez ran it then with the full EXAALT software stack on a fraction of the Summit machine, he was able to then estimate a figure of merit relative to Mira for the full Summit machine of 17x, and that's the red dot on the lower left of the slide. Now that was a pretty good number, but it's still far below the blue dashed line, which is our overall target for the EXAALT project, running on these 2 future machines that don't exist yet, the Aurora machine at Argonne and the Frontier machine at Oak Ridge, both of which are going to use GPU technology. So that dashed line represents a 50x speed up relative to Mira. And so we start out at 17x, and there were specific reasons why we were concerned about how likely it is that we were going to actually be able to achieve the 50x mark on these upcoming machines. Over the last year, through the collective efforts of the people on this presentation and several others that I'll mention, we were able to dramatically improve the performance on the Summit machine, so that now our figure of merit on Summit is over 200, which represents about a factor of 10 speed increase. And this is described nicely in an audio recording that was produced by Danny and is hosted on the Exascale Computing website, episode number 44. So a little bit more of a summary on what we actually did over the last year to achieve that 10x improvement. Well, the first thing was we got a lot of different people involved. So myself, of course, Stan Moore then got involved because of his role in the COPA project. But very important, we got special help under the NESAP project from NERSC, and that came in the form of Rahul Gayatri, who's an expert in performance optimization on GPU platforms. And he has done a lot of the work that resulted in this improvement. But we also got really good input from Sarah Anderson at Cray, and most recently, Evan Weinberg at NVIDIA has been making some very good improvements to the GPU performance. So the first step was to extract out all the complexity of the EXAALT software stack, including LAMMPS itself. So we basically threw out molecular dynamics, and we were able to boil everything down to a single force kernel that was standalone and had its own input data and its own accuracy testing that could be run and compiled very, very quickly. And so we call that TestSnap. And so the key thing is that even though it's very simple, it is still, because of the way we wrote it, very much representative of the real performance of the EXAALT application. And that definitely turned out to be true. When we started porting things back from TestSnap to LAMMPS, we got a lot of the expected performance back. So then within that TestSnap kernel, we were able to experiment with a lot of different things, including different GPU strategies, and also innovative ways of reducing the overall memory footprint and also reducing the number of flops even on serial platforms. So this resulted in a lot of good performance improvements, and then of course a lot of failures as well, but we picked the best of those and we ported them back to the LAMMPS code using the Cocos library, and that was what Stan was primarily responsible for. And then as a result of that, we were basically able to dramatically improve the overall performance on the FOM, because everything really depends on that single node performance. So a little bit more about what Snap actually is before I hand it over to Stan and Rahul. So at a high level, Snap is a machine learning potential, and it's one of sort of a whole class of machine learning potentials that have emerged over the last couple of years. And I've characterized that class by the blue dots in the slides, in the graph on the right. This is an interesting way to look at potentials, interatomic potentials in LAMMPS as a function of their computational cost and the year in which they were published. And so for a while, we were looking at this dramatic increase in computational cost of potentials as we moved through the last couple of decades. But interestingly, the machine learning potentials have broken this trend, and we're actually seeing sort of a somewhat reduction in computational cost, even though the accuracy of these potentials continues to grow as the methods improve, the amount of training data used to fit them is increased, and so on. On the bottom right there, I've just got a really high-level flow chart of how we fit a snap potential. Essentially, it involves taking a large number of small DFT configurations, passing them through LAMMPS to generate a set of descriptors for each configuration, figuring out what the best adjustable parameters are to match the forces, energies, and stress tensors in the training data is for one particular choice of that snap potential. And then using genetic algorithms to iterate over many possible choices for the hyperparameters. These are kind of more indirect parameters related to the overall structure of the snap potential. And in that kind of iterative way, by trying out lots of different potentials, we can find ones that perform very well in training, but also give good behavior in the applications of interest. So how exactly does Snap do what it does? How does it manage to closely match large data sets of DFT data? Well, the answer is essentially in picking a very, very general functional form, and that's represented by the two equations there in the green box. So the first equation indicates that we, first of all, decompose the total energy of the configuration of atoms into individual atom contributions. And then we add on a reference potential if we wish. It's not essential to do that, but sometimes it's useful. But the key thing is then that each per atom snap energy, that E sub I there, is written as an expression in a relatively large set of descriptors. And the descriptors are those large B symbols. Each of those represents a particular bispectrum component. The bispectrum components are rotationally invariant, translation invariant, permutationally invariant quantities, scalar quantities that essentially describe the shape of the local atomic environments that each atom sees. And I'm going to jump to the next slide now and give you a little bit more information on that. But I should mention that this work, this idea of using bispectrum components dates back to a seminal paper by Gabor Zani and co-workers published in 2010, which was the origination of their GAP approach to machine-learned interatomic potentials. And so we're building on a lot of their ideas, but we're using linear regression instead of Gaussian process regression, which gives us a lot more robustness in many regards and also greatly simplifies the fitting process. So what are these bispectrum components? Well, first of all, we need to recognize on the figure on the right that we're essentially assuming that the energy of each atom, the pink one in the middle, for example, only depends on nearby atoms out to some cutoff distance represented by the dashed circle. So we're looking for fingerprints of the positions of all the neighbor atoms within that cutoff distance, essentially trying to describe and characterize the shape of the local atomic environment. One trick we use, borrowed from GAP, is to take the 3D positions of neighbor atoms, represented by the green arrow there in the picture, and transform it from a radial distance and 2 angles to a set of 3 angles. So instead of sitting in normal 3D space, now the neighbor atoms are projected onto the surface of a sphere in 4 dimensions that's represented by 3 polar angles. The nice thing about that is by eliminating the radial coordinate, we now have something that is purely an angular representation, and we can actually use 4-dimensional hyperspherical harmonics as a way to expand the density of neighbor atoms on the surface of this 4-dimensional sphere. So this expansion, of course, is infinite, but we only take the lowest order basis functions in that expansion. We call these the U matrices, represented by the large U on the right of that second to the bottom equation. We sum those U basis functions for a particular value, index J, M, and M prime. We sum the contributions to the U basis function from all the neighbor atoms within the cutoff distance. We apply some switching scale factors to make sure that the contributions go to 0 for neighbors that are close to the cutoff. Then these little u basis functions that we obtain for a central atom are not rotationally invariant, and they're also complex functions. So that's not a good way to represent energy. We can obtain real valued scalar quantities that are rotationally invariant by combining these basis functions together in particular ways. And the way that we're doing it here is called the bispectrum. So for every set of 3 indices, J1, J2, J, we combine a whole bunch of these U basis functions in a series of nested contractions involving those H Clebsch-Gordon coefficients that are constants to obtain the final descriptors. Okay, so that bottom line is essentially the core of the SNAP calculation. If you want to, yep.
Aidan, it would now be a good time to ask you a couple questions that have come in.
Yeah, let's do it. Okay.
So one is, how will the approach work for non-homogeneous distribution of atoms in the system?
But that's really down to the training. As long as the training data that's used represents all of the different atomic environments that will occur in a non-homogeneous system, like, for example, a system that has surfaces would be a good example. As long as we're representing those surface structures and environments accurately in our training process, then it'll do just fine in those cases.
There's one more, and this came from probably right at the beginning of your presentation, but the person wrote, "This is my first ECP webinar, welcome. The material simulation, can it simulate adjustments in temperature or just at a set temperature reaction?"
That's really down to the role that temperature is playing. If it's only affecting the velocities of the mass nuclei, then there are essentially no complicating factors. If the temperatures are sufficiently high to actually excite the electrons, so that we're shifting the Fermi-Dirac distribution of electron states, then that is, I would say, an area of open research, because it sort of undermines the idea that we've got a purely conservative potential where energy and forces only depend on atomic positions. But in general, temperature is well represented within molecular dynamics simulation. I will say that.
Thank you. That's all for now.
Okay. Feel free to chime in later. I've got about I think three or four more slides, and then there'll be another break before I hand it over to Stan. So the bottom line is that equation on the bottom is at the core of the computation of the snap forces. But of course, that's the thing that contributes to the energy, and for forces, we need the derivative of this with respect to positions of particular neighbor atoms. And this slide just gives you, in a sort of a pseudocode sense, what that low-level force calculation looks like. And a couple of things to note here, and I apologize because the symbol, the notation here is different than what I showed you on the previous slides. But essentially what this shows is we've got a large set of nested sums going on. The dimensions of these sums are irregular. In other words, if you look at, say, eta, the range, if you look at the symbol mu, the range of the symbol mu depends on the value of eta, and so on for mu1 and mu2. So these are not regular square loops, nested loops, but they're rather more like pyramids. Secondly, the dimensions of these loops are not very large. So for the benchmark of interest for ECP, the maximum dimension is 14. And for some of the iterations higher up on the pyramid, the range will be less than 14, all the way down to 1. So this creates a variety of challenges when you're trying to parallelize this. I will say that a variety of people much smarter than me in terms of GPU optimization have worked on this over the years, but we've been particularly successful in the last year in coming up with innovative ways to refactor this set of nested sums to get better parallelism on GPUs. And so with that, I am going to hand it over to Stan, but before I do that, I'll just ask again if there are any more questions. Okay, Stan, it's all yours.
Okay, I seem to have lost the slides.
Yep, I can no longer share.
Okay, I'll pull them up.
Sorry, Aiden's got the token.
Oh, yeah, it's back. Okay, let me try that again. Okay.
Okay. All right. So Aiden did a good job describing the original CPU version of Snap, and Christian Trott from Sandia took this CPU version and he created a COCOS version in a proxy app called EXAMINI-MD. EXAMINI-MD was part of the COPA ECP project. It's a proxy for lamps, but only has a couple potentials. And if you're not aware, Christian Trott is one of the core developers of COCOS. He's also an expert on CUDA programming and GPU optimization. And when Christian ported the CPU version in lamps to EXAMINI-MD, he used several advanced COCOS features. So to expose as much parallelism as possible, he used hierarchical parallelism, and COCOS supports up to 3 levels. So you can see in the pseudocode on the right, the first level is the team policy, which is over the number of atoms. The second level is the team thread range policy, which is over the number of neighbors. So as Aiden explained, the first is the central atom, and then you have a spherical cutoff of neighbor atoms. And then the third level is over some inner loop that Aiden showed inside the bispectrum component calculation. Christian Trott also used shared scratchpad memory So for both threads and vectors, there was shared memory used. And this implementation was very memory compact, so it only used as much memory as the threads in flight. I took this version and ported it to the LAMPS Cocos package. And at this point, we weren't super happy with the performance, but it really wasn't clear if there was much room to gain. And so, next slide, please. So we did some benchmarking of this baseline version. So the dark blue is the EXA MD proxy app. The green curve is the LAMPS Cocos version. And the light blue is the serial CPU lamps. And you can see if you compare, so performance is on the left, and higher is better. And so if you compare a P100 GPU, a single GPU versus a Haswell dual socket CPU, we're slower on the P100, and this was not where we wanted to be. We thought we could do better, but we weren't sure how to get there. Next slide, please. Okay, so Aiden talked about EXAALT figure merit and benchmarking on Mira, and so I just wanted to go through that a little bit and explain how that's done. So as Aiden said, the figure of merit is a tungsten crystal using the snap potential. We ran this on Mira to get a baseline. And so the single node performance on Mira is then scaled up by the number of nodes on Mira. And just to clarify, I believe this was the CPU-only serial version. So this was not the Cocos version to get the baseline for Mira.
Yes.
Yeah. On Summit, we run 6 GPU replicates and 1 CPU replicate. So as Aiden mentioned, the EXAALT ECP project is not trying to run billions and billions of atoms. We're running small replicates, and then those trajectories are stitched together to form a very long trajectory, much longer than could be achieved with a single simulation. And so we run replicates on all of the GPUs on Summit, as well as the remaining 36 CPU cores. And so we did this for the version in LAMPS that Christian Trott wrote, and I ported to LAMPS. And when we benchmarked on Summit, we took the single node performance and then scaled that up by the number of nodes on Summit. This gave approximately 17x faster than the Mira baseline. And as Aiden said, the EXAALT PI Danny Perez has also run larger scale simulations to validate these numbers. Next slide, please. Okay, so we also benchmark the snap potential on other hardware, and something that was very concerning to us is that on CPUs, the fraction of peak performance has steadily been going down. So if you look at the table on the right, we're taking Intel Sandy Bridge as the baseline, and if you compare the fraction of peak on the CPUs between and Broadwell, it's going down. The GPU fraction of peak is not the case, but it's very, very low compared to the CPU fraction of peak. And so this was troubling to the EXAALT ECP project. And so one recommendation for a review in 2018 was to focus on Summit, focus on GPU performance, and see if we can speed that up as a stepping stone to the Exascale hardware platforms. And so this spawned a collaboration between the EXAALT ECP project, COPA, as well as the NERSC in order to see if there could be anything done to speed up snap on GPUs. Next slide, please. Okay, and so as Aiden mentioned, he created a standalone MiniApp that was based on the snap kernel and based on the CPU version, the serial version of the snap kernel. It's a proxy in both memory and computation. It doesn't have any of the communication. It doesn't have the molecular dynamics time integrator or anything else like that. But nearly all of the flops and memory are in this kernel. One thing that's very important is that it includes a correctness check. So obviously, it would be possible to optimize the code and get a very fast code, but have it give the wrong answer, and that's not what we wanted. And so this correctness check was just a pass-fail that was robust to make sure that there weren't race conditions or some other problems with the code. And we could have given the COCOS version to the NESAP program and asked them to start from there and try to optimize that. But we really weren't sure if there was much performance to be gained, and so we thought that, you know, if they were going to get performance, they needed to think outside the box. And so we didn't want to bias them with what we'd already done. And so we gave Rahul just the CPU serial version inside a MiniApp. And I will point out that the initial OpenACC port was very slow, much slower than the COCOS version on V100 GPU. And this just goes to show that this kernel is very complex. It's very non-trivial, but Rahul persisted, and I'll let him talk more about his work in TestSnap. But first, are there any other questions?
We've had a few come in, so probably back a couple of slides. Is the COCOS code the reason for this enormous gain on the Haswells, or was it the DL boost in the Xeon? Also, was the GPU code optimized by MathWorks GPU coder?
Okay, Aiden, can you go back a slide or two where we show the performance?
This one?
Yeah. Okay, so you're comparing performance on Haswell. So if you look at the light blue curve versus the green curve, they're approximately equal. And so this is saying that the serial version is approximately the same performance as the COCOS version. So I would say it's not the reason for the enormous gain. It's just there's a higher flop count, and so we get approximately the same performance with the COCOS version versus just the serial version. And no, I've never used a MathWorks GPU coder.
I'll just chime in on this on the first question. The fact that the person mentioned ZI, I think they may be referring to the Y array trick that we're going to mention briefly later, and so that certainly was that's a purely serial optimization in the computation, and that perhaps delivered like a factor of 2x speed up, but that means there's another 5x speed up that's entirely due to the parallel improvements in the COCOS implementation.
So there's one more question in there, Stan, and I'm not sure exactly which slide this is referring to, but it says eventually will calculating the distance, actually I can't read that, R_ij because of the nested for loops be the most demanding bottleneck of this approach?
I can answer that.
Yeah, go ahead, Aiden.
So for simple classical potentials that have been around for a long time and are very popular, like Lennard-Jones for sure, and to a lesser extent, say, embedded atom method, the calculation of the distances, pairwise distances, is certainly a major component. In the case of machine learning potentials, because of the extra layers of computation that occur after the distance calculation, typically that is not the bottleneck, and that's certainly not the case for SNAP.
Yeah, just to add to that, the IJ loop is at the very top, and then you've got many, many levels of nested loops below that, and so it's not significant for SNAP.
Yeah, and another way to answer that question is to ask the the audience member to look back at the earlier slide I showed showing increase in computational cost as a function of publication date of different potentials. There is a really huge growth in that cost over the last couple of years, and that's not because of increase in the number of neighbors. The number of neighbors has stayed roughly the same, and so it's really because we're going from simple two-body potentials to much more complicated many-body potentials.
Excellent. Those are the two questions from that section. Thank you.
Okay. I'll jump to the next slide then. And Rahul, do you want to take it from here?
Can you go one slide
Sure.
previous to this? Yeah, hello, thanks Dan and Aidan. Hello everyone. So I joined the EXAALT project in January of 2019, and we started working on the testnap as a part of the COE hackathons that happen at NERSC every quarterly for ECP applications. I wanted to go back to this slide because I just wanted to reiterate the importance of having a proxy small app like testnap in this case for really concentrating on all the crazy ideas that we can try before actually sticking to one that works. So in those 4 or 5 days of hackathon, it was really essential that we don't get bothered down by the baggage that comes with LAMPs and the big LAMP snap applications along with the COCOS implementations. Although we started this proxy app as a small test case for the hackathon, over the last 1 year, this has developed into a nice small mini project where we have implementations, parallel implementations for testnap in almost every programming framework for GPUs like OpenACC or CUDA or OpenMP Offload and COCOS. And we are using this as a test case for a lot of our other projects at NERSC. Like one of the main projects there is testnap is now a part of the application suite that we have provided to the PGI compilers team, where they are developing the OpenMP Offload capabilities for their compilers for the next machine that is going to come at NERSC, the Perlmutter machine, which has NVIDIA GPUs. And testnap would be one of the applications that will test the effectiveness of the offload implementation of the compiler. So I just wanted to reiterate how important this testnap was for the progress that we made during the last year. Yeah, next slide, Aidan. So when we started working with this testnap, the initial big contribution came from Sarah Anderson, who was our mentor at the first January hackathon. So if you see on the left side, which is the typical algorithmic structure that Snap has for every atom I, it iterates over every neighbor J, and then each of the work that is done over this atom and neighbor pair that Aidan and Stan discussed in the previous slides is happening one after the other. And this this was how the COCOS implementation also worked, like as Stan talked earlier, where the atom I, if you just look at the GPU terminology, every atom was, the work of every atom was distributed across thread blocks, and then hierarchical parallelism was used over the neighbor loops and the innermost loops, where the neighbor loop was distributed across the threads within a thread block, which is the thread vector range in COCOS, and then team thread range in COCOS, and then the vector range was used in the inner loops. So this had some problems where first it increased the complexity of the code, and then the second thing, it gave, although this was very memory compact implementation, we had issues that it was oversubscribing the resources that were available on a GPU. So Sarah Anderson from Cray suggested that we actually break up the work across atom and neighbor dimensions, as you can see on the right side, where every atom and neighbor pair perform the first function, and then they go on to perform the second function. So this is a bit counterintuitive from how CUDA work is generally done, where we actually collapse the work into a single kernel to optimize on the kernel launch latency. But the work inside each of these functions was large enough that this launch latency was quite negligible in this case. Although the one negative aspect of this change was that we had to now store the atom and neighbor specific information across different kernels. And this increased our memory footprint tremendously. Next slide, please. So by the end of the first hackathon, by that week, we were able to break the kernels and distribute the work of atoms across the atom dimension across the thread blocks and threads within a thread block. And this increased our memory footprint, yes, as mentioned earlier. But even though we worked only for one week on this, we were already decently close enough to match the baseline LAMP snap performance. So if you see on the left side, the figure shows the red bar shows what is the baseline performance. We normalized the results over the baseline performance. So over the next few set of slides, you will see the baseline performance as 1, and the green bar would show you how the test snaps performance was improving over the baseline. So the lower you get, the better the performance, right? So we were less than 2x slower than the test snap. The test snap was less than 2x slower than the baseline performance by the end of first week itself. Next slide, please. So then we applied the same test technique and distributed the work even across the neighbor dimension, and we were within the competing distance of the baseline performance. But a disadvantage of this was that this greatly increased our memory footprint, because now we had to store both atom and neighbor specific information across the kernels. It increased so much that we could no longer fit the figure of merit benchmark problem within the GPU memory, which is 16 gigabytes. And next slide. Okay, this is where I give the talking back to Aidan, where he'll explain how we overcame this problem.
So after this initial pass, where we started to see some good results from the breaking of the kernels, but we were running into problems with very large amounts of memory being used, to the point where we couldn't fit the large FOM benchmark problem into memory. I started looking again at the serial code to see if there's things that we could do to reduce the memory footprint, and indeed there was a lot that could be done. A lot of these multi-dimensional arrays are not compact, and there's a lot of empty space that's basically not used when you pack them into say a 5-dimensional rectangular box. So by compacting those down into 1D arrays, we got about a 20x reduction in overall memory usage. Another key innovation was the rearrangement of the loops that we're calling the Y array trick, and this was an idea that emerged from discussions within the EXAALT project. I want to make a shout out to Nick Lubbers, who has been looking at combining SNAP with neural network approaches, and when he was trying to figure out how to combine the low-level bispectrum derivatives with the gradients that are generated in a neural network, he started to think about ways to rearrange things, and just for the purposes of getting his stuff to work. But he also realized that there could be a big performance improvement, and it turned out he was exactly right. I've got a slide on that, I think, right here. It's a little bit complicated and we don't have a lot of time, but I'll just point out that in red on the left, that we basically went from a final derivative or gradient calculation with a computational complexity of j to the 5th down to one that is j to the 3rd. And j in this case is that maximum array dimension that I mentioned earlier, that's typically of size 14. So we're basically going from 14 to the power of 5 down to 14 to the power of 3, which essentially wipes out the cost of that final derivative calculation. So the product of y times del u, it becomes very, very cheap. And all that we're left with is the underlying cost of calculating the prerequisite quantities, which is basically the Z matrix and then the Y matrix. So there's some, and what's really fascinating about that is it actually basically eliminates the dependence on the number of neighbors. So most of the computation is now involved in things that do not depend on the number of neighbors, which is very unusual for an interatomic potential, where generally we are slaves to computational cost increasing with the number of neighbors. In practice, that just in serial calculations, that Y-array trick across the board gives about a 2x speed up. Although, interestingly enough, we went back and ran our Mira benchmark, and we're very surprised to see over a 5x speed up on Mira. And some of this may be due to the fact that we've also got a greatly reduced memory footprint, which might have been contributing to some performance loss on Mira, and that went away as well. So with that, I'm going to let's see. I think at this point I need to hand it back to Rahul, right?
Yes.
Okay.
Yeah. Hi. Yeah. So with that trick, we were now able to implement. So Aidan had already made a version of implementing the Y-array trick in TestNav, and with that trick, we were now even able to fit the bigger problem size, the figure of merit problem size, into the GPU memory, and we started applying the same techniques that we applied to the smaller problem size onto the bigger problem size. At this point, I just want to mention that we went through a lot of different using a lot of different frameworks to expose the parallelism on the GPUs. Like, as initially we started with OpenECC because it was much easier to start there. We could just distribute the atom and neighbor loop across the thread blocks and threads. Then after a certain point, we switched to a CUDA implementation because we wanted to expose a higher degree of parallelism using multidimensional grid. And then currently we are now working on a COCOS implementation of TestNav because we wanted to keep it consistent with what the Snap implementation is available in the LAMPS package. Next slide, please. Yeah. So the Y-array trick helped, as Aidan mentioned, the Y-array trick helped a lot even without the other CUDA optimizations. So for example, initially, if we distributed just the atom dimension across the thread blocks and threads of a GPU, we were still slightly slower than the baseline LAMPS implementation. But if you see here, just with distributing over the atom loops, the work of the atom loops, we were already similar to the LAMPS baseline implementation. Next slide, please. And as soon as we distributed the neighbor loop across, added the parallelization over the neighbor loops, we gained much more speed up compared to the baseline. But we now have a memory footprint of 12 gigabytes, which is still high, but later on even that came down quite a bit. Next slide, please. So one major difference between GPU and CPU programming is the way the data is accessed. On a CPU, you want the data to be laid out in a row major fashion so that we avoid fault sharing in caches. For example, if you see on the left side, let's say we have a matrix and we distribute different matrices across different cores for working. So each core would, and we store the data in a row major fashion. The core 0 can get like 4 or 5 elements, depending on what elements are, into its L1 cache, and L1 and core 1 can then do similar in its own L1 cache. If we store the data in a column major fashion, we might have, even though the cores might not be working on the same element, but because they are present in both the core 1 and core 0's caches, it might lead to a lot of cache flushing, which is what we call as fault sharing. And we want to avoid that on CPUs. But we want that, like on the right side, if you see, we want that on GPUs because the way the GPUs work is that there are generally 32 threads within a GPU warp inside a thread block, and all the 32 threads perform the same instruction in one clock cycle. So you want all the data needed by all the 32 threads to be as close to each other as possible so that we avoid time spent in getting these data onto the GPU cache for the thread blocks. So you want, this is called memory coalescing, and you want a column major format of data storage on GPUs. So next slide, please. So just by changing the data access pattern in testnap for GPUs, we got a 2x performance boost immediately, as you can see from the figure shown here. Next slide, please. The other thing that we did was, if you see that we on the right side, on the top right side, that we reversed the loop order, where we initially we used to do the atom loop outside and the neighbor loop inside, and then now we reverse the order, making atom the faster moving index, and then the neighbor loop. This was much easier to do because we split the kernels up, and it became a simpler process in this case. And this change gave us another 2x performance boost. Next slide, please. As I showed in 2 slides earlier, where we changed the access pattern from row major to column major for all the data structures. The issue was that in one of the major data structures, the U array, which even Aidan talked about initially when he was explaining the algorithm, the U array is being used in 2 different kernels, one of which has an atomic operation on the U array, for which on GPUs it would be better if we have a column major access. But on the other hand, on the other kernel, the access pattern was so different that it was much better to have a row major access on the GPUs for the U array compared to a column major. So here we had to make a trade-off, where if we make a row major, if we store the U array as a row major in the row major format, we were losing approximately 10% of performance on the kernel that was performing the atomic operation, but we were gaining approximately 25% on the other kernel that I just spoke about. So we had to make a trade-off, and we got another overall 15% improvement in the overall timing. Next slide, please. So this was our so the EXAALT snap application got selected for the next round of the hackathons that happened in July in Oakland, and we were, by that time, the test snap was already 7.5 times faster than the original baseline implementation. And so at this hackathon, the idea was to get the baseline lamps perform similar to the test snap performance. And at this point, I'll give the talking back to Stan, unless somebody has any questions.
Okay, thanks, Rahul. Aidan, can you go to the next slide, please? Okay, so as Rahul said, the focus of the July 2019 hackathon was to port the improvements in test snap back to lamps. So I do want to mention that during the hackathon there was additional optimizations added to test snap, and so I didn't completely catch up, but I did port some of the improvements. And so I broke up the kernels, and as Rahul mentioned, this led to a lot of memory increase, and it actually made the code slower at first. It's possible that this was due to a suboptimal memory layout. So as Rahul mentioned, typically on GPUs you want a column major, or what Cocos calls a layout left. This is actually not true if you're using hierarchical parallelism. So it wasn't that we had never tried that or thought about it, but because we were using hierarchical parallelism, we needed a layout right or a row major to get the optimal performance. And so when we broke up the kernels, that changed. It was actually a little bit unnerving, but because we had test snap, we had assurance that continuing down this crazy path, or what seemed like a crazy path, would be fruitful. And so we had to store a lot of extra memory. And then as Rahul said, it used up a significant portion of the GPU memory. And so we couldn't actually run large problems with this new implementation until we chunked up the loop. So we actually would only process 2,000 atoms at a time. And that way we were able to keep the memory cost below the limit of the GPU memory. And then we added the column major and the loop reorder. And finally, when we got to the loop reorder, we saw the significant speed up in lamps, COCOS, that we saw in test snap. But it really wasn't possible to do this loop reorder without breaking up the kernels first. And in the process, we removed a lot of the advanced COCOS features. So we replaced the hierarchical parallelism with flat parallelism, as well as collapsing some of the loops. And we got rid of the shared scratchpad memory. And so we did benchmarking, as I mentioned before, on Summit. And previously we were 17x faster than the baseline. And the new code after the end of the hackathon was 90x faster than the Mira baseline. So we got a little over 5x speed up by taking the optimizations in test snap and putting them into the COCOS version in lamps. Next slide, please. And as I said before, there were some additional optimizations that were added during the hackathon. I didn't have time to catch up, and so those were added later. Some of these included changing the memory layout of the indices, so using complex numbers and multi-dimensional arrays instead of arrays of structs. So just kind of optimizing the axis patterns. And then we also took out more of the hierarchical parallelism and replaced it with flat parallelism, collapsed some more loops. And then, as Rahul mentioned, there was one kernel, there was one array that for one kernel wanted to be one layout, and for another kernel wanted to be a different layout. And so, because these are so computationally expensive, we could do a transpose between the kernels and actually get a speed up. And so adding in these additional improvements from test snap, we got a little below 8x speed up. And this is cumulative, so this includes the 5x speed up previously. And so we were now 134x faster than the original Mira baseline. Next slide, please. And Rahul has not stopped since the hackathon. He's continued to work on test snap. So transposing data, also using 128-bit load stores instead of the normal 64-bit load stores, using a double 2 vector type, as well as reducing the memory footprint. And so since the July 2019 hackathon, he's gained over 2x speed up in test snap. Not all of this has been ported to the COCOS lamps version, and so we still have some more work to do. Rahul, do you want to add anything?
No, no, not right now, no.
Okay, next slide, please. Okay, and then looking forward, we've actually got some help from NVIDIA. So Evan Weinberg from NVIDIA has also been working on this kernel. He's actually been working on the lamps version instead of test snap. And some of the things he's done is refactoring some of the kernels to avoid atomics. And he added back in a judicious use of hierarchical parallelism and scratch memory. So as I said before, we originally had it in Christian Trott's version. We took it out with test snap, but then Evan added it back in some places. This new version is being tested. It's not released in labs yet, but will be released eventually. And we actually had a chance to benchmark this on Summit, just like all the other versions. And this gave a cumulative 12x speed up since the original baseline COCOS version, giving a figure of merit projection of 210 over the Mira baseline. And, you know, we're not done yet. I think between Rahul and Evan and Aiden and myself, we've got more work to do. Next slide, please. Okay, so these are just a few of the lessons learned, but the performance gains came from both algorithmic improvements, so that would be like the Y-array trick, which changed the serial version of the code, as well as implementation improvements that changed the CUDA or the COCOS version of the code that were targeted towards GPUs. So we needed both, and sometimes one opened up or helped the other improvements. As we've said before, the small test snap proxy app has been absolutely critical in this process. It allows rapid prototyping. It has a correctness check, and we can give it, to vendors. We can give it to our collaborators. It's small. It's portable. It's standalone. It's just been, I think, one of the keys in enabling this performance improvement. We did profiling. We did a roofline analysis as part of the hackathon. So that's very helpful. And I think the one lesson that I take away from this is pay attention to memory access on GPUs. I think not all of the things that we've done to the snap kernel are applicable to all kernels, because snap is so computationally heavy. We can hide launch latency. We can hide, the cost of a transpose. That may not be true in lighter weight kernels, but it was true in the case of snap. Next slide, please. And here's the last slide. And if you want to learn more about the machine learn potential snap or some of this work, we'll leave these links up. And with that, we'll ask for any other questions.
So there are no other questions at this time. So I'm going to take control, display the last slide. And while that's occurring, I just want to say thank you. That was very interesting. I really appreciated your time today. Before everyone goes, I know we're a little bit over. I just wanted to remind you that, sorry, I'm getting the slide up. I can't talk and do at the same time. I'm not that talented, but so I want to thank everyone for participating today, especially thank our speakers for putting this together for us. Obligatory survey time. The folks that fund us actually do ask for the survey results. It is important to the people that give us money. So if you like these webinars, I really highly encourage you to go to that link and take that survey. It's 5 questions. It won't take more than 2 minutes of your time, but it does give us, suggestions for future webinars, and it also tells us if this is a good format or not, but it also helps our program sponsors see that people care about this series. And then finally, the slides and the recording will be available on these 2 links within the next week or so. And then the next webinar in the series is going to be on February 19th, Introduction to COCOS. You heard a little bit about Christian Trott during the talk today. So if that's interesting to you, we highly recommend you go ahead and register. We do have a 200-person cap, so ensure you get your ticket by registering soon. Again, thank you everyone today. I really appreciate your time. And with that, I will end the session. Thank you.